Good afternoon, friends. This is Abhijit from IIT Madras, and I'm going to be your instructor for the next 3 sessions in under the QEEE program, and we are going to talk about spur gears. Okay, so without much of an ado, let us begin the contents of this talk. Yeah, so here is what we are going to talk about. We are as the title of the talk suggests, we are going to talk about spur gears. So at the introduction, we will talk about why do we need gears in the first place. We'll have some motivation as to why gears form a very important machine element for different applications, and why is it that gears find so very all pervasive applications in engineering as of today. We will then dissect out different parts of the gears. We will introduce the terms and terminologies associated with the spur gears. The spur gear nomenclature would be elaborated hopefully by the end of the day today. Next day, that is in the next session, we are going to talk about involute gearing in particular, and hopefully we will have time left in the final session to talk about gear trains. So that being the agenda, hopefully at the end of these 3 sessions, you will come to know about the importance of gears in different transmission systems and in different machines. That is the first objective that I would like to set for ourselves. We would also know the different types of gears that are used in applications that will be elaborated through the talk right on today itself. But the predominant portion of this material is going to concentrate about the geometry of the gear tooth. It is not very obvious that there is a very special geometry involved in the gear tooth, and that speciality is very important from the kinematic perspective. So, we are going to have a lot of elaborate discussion as to why that geometry is required in the first place, and what is it about gear tooth geometries which really is important. So, even from the application perspective as well as from the manufacturing perspective. So, we are going to have all that discussion, and at the end of the course, hopefully you should be aware that what is the gear tooth geometry that is typically used in application, and what is the need for such geometry on the gear tooth. And also we are going to do lots of analysis of input output characteristics of gears and gear trains. Different problems are already posted in your assignments and multiple choice questions. You will be able to work those out hopefully with the theoretical background that you will gain from these lectures. Okay, so let us first understand the crucial part of a machine. Obviously, a machine is required to do some work. So, therefore, as per the first law of thermodynamics, law of conservation of energy, power is required for any machine to operate. For any machine to operate, it is required to be powered, and this power is usually provided through either an IC engine, as in the case of automotive example, or through some turbine, fluid power, or steam turbine. It could be gas turbine also, and even it could be electrical motor. So, in all these examples, what you will have is that what is typically called a prime mover. A prime mover is the source of power for that machine. The power is given to the machine to operate through this prime mover, as is true for the diesel engine or petrol engine, gas turbine, steam turbine, hydraulic turbine, electric motor. These are all examples of a prime mover. But if you look at it carefully, the output of any of this prime mover or engine, if you may like to call it, is basically a rotating shaft, and that rotating shaft conveys the torque as well as a rotating speed. Because it is a rotating shaft, it has to rotate. Along with the rotation of the shaft, a speed is conveyed. So, anything which this rotating shaft, which is let us say the crankshaft of your engine, anything with which this crankshaft is getting connected will rotate at an identical speed. And also what is probably a little difficult to fathom other than the rotating speed is the fact that along with the rotating speed, what is conveyed is a torque. It is a this torque, or the driving torque as we would call it, is the one which will work against the load torque and create the necessary motion for our For example, in the case of automobile, it is this driving torque which acts against the load torque and thus produces motion. So, this is elementary, that you definitely have a prime mover or an engine which produces the power, but the power is itself, if you recall engineering mechanics, power is given as a product of torque and rotating speed. So, basically the output of any engine will have two important constituents. One is the torque, the second is the rotating speed. The rotating speed is obvious, you can visualize that because the shaft is rotating, there is a speed associated with it, but there is also a torque which comes from the engine to the gearbox or to the load, whatever it is. So, there is this torque and rotating speed which are supplied by the engine to the output side, and this product of torque and speed is essentially what is power, as we learnt in our elementary engineering mechanics course. So, that is the first part with of the machine, which is the prime mover or the engine in general. But now, if we think carefully about the different kinds of machine that we have in applications, let us take one example. Here we get to see a crane, a mobile crane is schematically illustrated in this figure. What you see is that the purpose of this mobile crane is obviously to lift load, right. But the owner of this mobile crane would definitely like to have an objective that he wants to lift as high load as possible, and he also wants to lift this load as quickly as possible, because obviously he has paid for the mobile crane and he wants this mobile crane to do maximum possible work. So, this maximum possible work can arise in two different contexts. The demand from the customer could be that one has to lift maximum possible load. This in turn means maximum amount of torque should be supplied from the engine such that maximum load is being able to be lifted through this hoisting mechanism. So, the torque must be able to do the work against the load. If you increase the load, the torque requirement is going to enhance. Also, you require that this load be lifted at the fastest possible speed, so that the work gets done quickly, and whatever it is work is associated with this mobile crane can quickly undergo completion, in which case the mobile crane can be profitably deputed in some other application. So, again dictated by the economics of the application, you require that this load be hoisted as quickly as possible, which means that the speed of hoisting should also be very quick. Again, that dictates that whatever is driving this mechanism, it definitely is an engine or in general a prime mover, the rotating speed associated with those pulleys should be as high as possible. So, definitely you want the machine to work, which means you want power. The power is fed by the engine. You also want to lift the highest possible load, which means you want the high torque coming out from the engine. You also want the load to be lifted at fastest possible speeds, which means that the output speed coming out of the engine should be as fast as high as possible, and you all want it at a minimal cost. That means all of this should be attained with the minimum fuel efficiency, with the minimum fuel cost associated with the burning of the fuel within the engine. So, the requirements are really steep if you look at it from the perspective of the owner of this machine. You want you want all the different factors which the machine is designed for, all of them we want it together. Okay, I will take one more example probably to illustrate this aspect. This is a machine which is our usual lathe machine. You would have seen that in workshop. Obviously, the purpose of a lathe machine is to remove material. So, you wish to remove during a turning operation, for example, you wish to remove material and you wish to have a maximum material removal rate, so that you quickly finish the job and deput the machine to another productive job. So, to have a maximum metal removal rate, you could do it in two ways. You could rotate the spindle holding the job as fast as possible, or you could have a high depth of cut. Now, you can understand if the depth of cut associated with the tool is high, then the load, then just try doing this experiment yourself, that if you increase the depth of cut, then beyond a point obviously the spindle will not be able to rotate, because the requirement of the driving torque to overcome the load will not be satisfied, because the load will increase and the driving torque given by the motor which runs this rotating spindle is limited. The maximum driving torque is limited. So, at some point you will not be able to take a depth of cut greater than what can be delivered by the motor. So, depth of cut obviously increases the material removal rate, but you cannot achieve the depth of cut beyond a certain point. Beyond a certain point, the load torque will increase and the driving torque will not be able to supersede the load torque. As a result, you will be limited to have a depth of cut within some reasonable value. Similarly, the other requirement is you want the speed to be as high as possible, because the speed of the job will ensure a greater material removal rate. So, both of these basically boil down to the requirements of the motor itself. The motor must be able to have an output of high torque as well as high speed, right, and you also want the motor to consume the least amount of electrical power, right. So, all of these things are what is demanded by the customer. I will take one more example now, which is from our automotive engines. Okay. So, automobiles, as you know, are one very important case where gears are being used. So, let us take a look as to why we need gears in automobiles. So, first again let us do this analysis, this simple analysis, that what is the requirement of an automobile. Obviously, to drive the vehicle you need power. The power comes from the engine, but the question is, it is not just power, it is also this torque and speed which is required from the engine, right. For example, as you see in this picture, this vehicle is negotiating a steep upslope, and as the vehicle negotiates a steep upslope, a very high resistive load is encountered, because it has to work against a component of its own weight, right. So, just like while cycling uphill, you get to you almost feel that someone is trying to resist you back. You are not being able to climb the uphill so very easily. The same thing is felt by the vehicle which is negotiating a steep uphill terrain. There is a very high resistive load. So, the engine associated with this automobile should be able to give that load torque which counters this resistive load, otherwise the vehicle will not move uphill. But in some other cases there may be a downhill terrain or there may be a flat terrain, in which case the load requirement is not so high. When in comparison to this situation, as you see in this picture, if you contemplate the situation when this very same vehicle with the very same driver is driving on a plain terrain, the requirement of the driving torque is not so very high, because the load torque is much lesser as compared to the uphill terrain. So, the moral of the story is, while driving a vehicle, the requirements of torque that has to be supplied is going to be different depending upon the terrains which the vehicle is undergoing. Also, for a commercial vehicle, when the commercial vehicle is operating in the full load condition, the load associated with moving that vehicle will become high, as opposed to the case when the commercial vehicle is running empty, right. So, therefore, the moral of the story, as I said, is that the vehicle, to be drivable at diverse road condition, it has to counter a wide range of load torque, right. This is something that the vehicle manufacturers are aware of, and they have to design their vehicles such that depending upon the diversity of terrain for which this vehicle has to be used, there must be some suitable arrangement by which this diverse torque can be provided by a certain mechanism within the engine, and this happens to be the gear. The other counter example from the speed perspective, if we talk, again depending upon different drivers, here we have a small cartoon showing two different drivers. One very young and adventurous driver, he likes to ride his vehicle at a very high speed, whereas another driver who is very calm and probably takes life little easy. In such a case, this person is driving very slowly. So, again depending upon the driving habits as also the road conditions, you may have different requirements of speed from your automobile engine. So, there are different requirements of speed, there are different requirements of torque owing to different driving conditions on the road, and the automobile manufacturer has to make sure that all these different requirements are not only met, but they are met with a minimal cost. So it is not just obvious that the vehicle manufacturer can need to provide an engine which supplies all this torque and all this speed, but it must provide a mechanism such that all this diverse torque and diverse speed can be supplied from the engine transmission system at minimal cost. That is very important, and the trouble lies here. Once you talk about cost, there is a small little trouble. This is what we call the fuel consumption chart of a typical engine, right. So what you see here on the x axis is the speed, and what you see on the y axis is the brake mean effective pressure, which basically is a function of the torque. In some way it relates to the torque, and these contour lines that you see on this figure are basically the values associated with the specific fuel consumption. So what it shows is that this fuel consumption is least at a very small range of speed and a small range of torque. So the fuel consumption will vary if the torque and the speed varies in an engine. So the customer rather wants a varied torque, the customer wants a varied speed, but also the customer wants a varied torque and a varied speed at minimal possible cost, right. And the minimal possible cost of running the engine happens to be in this zone, wherein the torque and the speed is a very, very narrow range. You cannot supply that much diverse torque and diverse speed within that narrow band of operation. So if the engine has to be economically operating, it is imperative that some other device is envisaged such that the engine keeps running at this amount of torque and this amount of speed, but something else, which is precisely the gear, will supply the diverse amount of torque and the diverse amount of speed associated with the different operating condition. This is exactly what is done by a gear. So please understand, the engine in itself is a powerhouse. The engine does provide power, the engine does provide torque, the engine does provide speed. But the problem lies is in this fact that whatever power, torque and speed the engine provides is in the optimal running conditions of the engine is such that the torque and the speed bandwidth is pretty low. It cannot satisfy the diverse requirements of the driving conditions on road. So to ensure that the driving conditions in road are met, the diverse driving conditions on road are met, we need to contrive a certain application which can scale up this bandwidth of available torque and available speed, and thereby offer the user the diversity that he or she wants as he or she drives the vehicle. So this is exactly what we will see is done by the gearing arrangement. So just to complete this slide, as I said, for economic viability the engine should run within a very narrow range of torque and speed, which is precisely this range, right. You see that the fuel consumption increases drastically as you surpass this narrow speed. From 275 it goes to 290 and then it crosses 300 pretty quickly. So if you in fact want to run the same engine without any gearing arrangement, without any transmission arrangement, what will happen is that the fuel consumption will drastically increase and the economics of the entire operation will break down. So the user demands of the wide range of torque and speed cannot be economically met by the engine alone. Therefore, you need some supporting structure, which is basically the transmission, which is what we are coming at. So this course is going to be about the gears, it's not going to be about the engines, but I thought it is important to understand the link between the engine and the gear so that you are able to better appreciate the usefulness of the gear application. So here is a simple schematic of a gearing arrangement. So what we do is the following. As I said, the engine output shaft provides a certain torque and a certain speed. I call torque as T and speed as omega, right. So what we do is we attach this engine output shaft with a gear of radius D and mesh this gear, or rather I mean, if I don't use this technical word mesh, I what I do is that I engage this gear along with a larger gear, the diameter, the size of which is n times d. The size of the gear which is mounted on the engine output shaft is d. The size of the gear which is in contact with or in engagement with this gear is n times d, right. What turns out is that the output shaft which is mounted on this gear, right, is the which is connected to this gear will deliver an output torque which happens to be n times t, and it will have an output speed which happens to be omega by n. So, the output from this arrangement will now be n times t and omega divided by n. So, in other words, if n is positive as is shown in this figure, and as is the case, that you will see that the torque supplied by the engine can actually be scaled up, right, if n is a number greater than 1 as is seen in this picture. So, the torque whatever the engine is delivering can be scaled up by a gearing arrangement, but since a gearing arrangement has to follow conservation of energy associated with an increase in torque, there has to be a equivalent reduction in speed. You cannot ask for both torque and speed together to be increased, because if torque and speed together increases, that is virtually saying that new energy has been produced. That cannot happen. Energy can be produced only at the engine level, which happens also because of burning of the fuel. Whereas in the gearbox there is no fuel that is getting burned, so energy cannot be produced, right. So, whatever is the energy supplied, that has to be the same as the energy output, that is assuming that there are no losses in the transmission. In fact, practically compared to the engine, transmission is a very efficient device, the losses are quite minimal as compared to the engine. So, getting back to the point is the T times omega is power which is supplied by the engine, and the power which is available at the output shaft, this black shaft, is n times T into omega by n, which means it is actually the same power which is available, but the trade off between torque and speed can now be attained simply by sizing this gear. By playing with this number n, I am able to have whatever torque I want. I will be sacrificing the speed, that is correct, but whatever torque I want I can attain simply by going with different values of n, and this is exactly what happens in a car gear. If you have observed the driving of a car, and some of you may have yourself driven a car, you will understand that in first gear, or rather when you have to go that uphill terrain, you are basically in the first gear. In the first gear, this n value is pretty large, which means that the driving torque which comes out from the transmission and goes into the wheel axle is actually large. It is large enough so that it can supersede the load torque requirement, and as a result, when you are going for in an uphill terrain, you are going to go in the first gear. What happens in the higher gears, let us say third gear, fourth gear, fifth gear, this n value keeps on decreasing, and as n value keeps on decreasing, the torque requirements or the torque delivery is decreased. Because the vehicle is already running fast, the load torque associated or the resistive load as the vehicle faces is not so high, and as such you can come down to the driving torque requirements and increase the speed if you want. So, it is always this trade off between torque and speed which keeps happening every time the driver changes his gear, and also you have automatic gearing system. Even in those automatic gearing system, this is the trade off which happens within an electronic controller, for example, and in those cases also it is just the torque and the speed balance which is being played with, right. So, anyway, we are going to stick with manual transmission and spur gears more particularly, but you must understand that at least from the automotive context, the reason why we have gears is to enable the vehicle to supply different torques and different speeds as per the requirements of the driving conditions. So, keeping the engine torque and engine speed in the optimal range, a wide range of output torque and output speeds can be obtained using the gear. So, simply by changing this value n. So, associated with a 5 gear transmission system, you will have 5 different values of n, each will engage at the time the driver engages the lever associated with the gear, and each time this value of n will change, and as a result you will get different torque coming out from your power house of the engine transmission taken together. Okay, as I said, power produced by the engine is equal to the power consumed by the load. So, definitely there is nothing, no power which is getting manufactured or which is getting destroyed also at the transmission. So, as I said, the transmission losses are supposed to be minimal, but yes, there are transmission losses. If you ignore the transmission losses, then you can make the simplistic argument that the power produced in the engine will be equal to the power consumed at the load level, which is basically the output of the gear. Okay, so owing to this reason, gears occur in a wide range of application. They are ubiquitous. Automobile being one of them. Even in your lathe machine, you have gears. There are many different applications where gears have to be there, simply because of this reason that machines are not designed for one condition, they are designed to be operating on diverse condition. The power requirement of the machine is met by the engine, but the torque speed balance requirement cannot be met by the engine, at least from an economical standpoint. So, from an economical standpoint, it is imperative that the engine be clubbed along with certain gearing systems such that the diversity of the torques and the speeds that can be tapped in through that engine system increases manifold. So, gears are so very all pervasive that even your Make in India logo, you can find it's all, this lion is made up of just gears. So, gears do occupy a very central and pivotal position in engineering. I have seen most of the engineering college mechanical festivals, mechanical engineering festivals, including the one at IIT Madras, use a logo which have something, some pictorial form of gear depicted in it. So, that is the reason why gears are very, very important, and rightly so. It has found its place in most of the logos associated with engineering. Okay, so with that little introduction, let us now get into the heart of the topic. We will first study an elementary concept, that of a friction disc, and from the friction disc we will move on to what is technically called as gears. So, here we are seeing two discs, basically one in blue and the other in red. The sizes of the two discs are shown as R1 and R2. What we mean by friction disc is the following, that when these two discs are rotating, the point of contact is at a no slip condition. What is meant by no slip? It means that the point of contact, whether you assume this point of contact to be a point embedded in this blue body or a point embedded in the red body, either way the velocity is going to be the same, right. So, that is basically the no slip condition. Whenever you have two bodies in no slip, that means the point of contact between the two bodies will have identical motion, whether you assume the point of contact to be embedded in one body or the other. So, that is technically what is called a no slip condition. So, if you have enough friction between the two bodies, then this condition of slipping will not arise and you will have the no slip condition. So, when we say that these two bodies are friction discs, we essentially mean these are two discs wherein there is enough friction between them such that the no slip condition is always satisfied. And if there is a no slip condition that always satisfied, what we will have is that the point of contact will have the same velocity, whether you consider the point of contact to be associated with body 1, that is the blue body, or body 2, which is the red body. So, this is what is called the no slip condition. And essentially, if you assume the point of contact to be embedded in body 1, then the velocity of the point of contact is omega 1 r1. The linear velocity is angular velocity times radius. Similarly, if I assume this point of contact to be embedded in body 2, then the linear velocity of this point of contact would be omega 2 times r2. And as I am saying that by our very assumption that it is a friction disc situation, which essentially means that there is ample friction so as to ensure the no slip condition, and the no slip condition in turn means that the velocities will be same. This essentially boils down to the requirement that omega 1 r1 is equals to omega 2 r2. So this is exactly what we will get even for gears. So therefore it was worth discussing this fact. But now you can understand that how the gearing arrangement will work. The idea of increasing the speed or decreasing the speed can be very easily attained through this. For example, if the input rotating shaft which is connected to the engine is this blue disc, the input shaft, on the input shaft we have mounted this blue larger disc, right, and on the output shaft we have mounted this red smaller disc. Then what will happen, because of this omega 1 r1 is equals to omega 2 r2 requirement, is that you will get to see that omega 2 is larger than omega 1. So the speed can be increased if the input is connected to this shaft which is holding the blue disc, and the output is taken from the shaft which is holding the red disc. So you can get any speeds if you want, and again by a law conservation of energy, by whatever factor you gain speed, you will drop the torque, because you cannot gain both speed and torque together. If you have gained speed by a factor of 2, then you would have to lose torque by a factor of 2 again. So that is a rule which you cannot play with. The total speed torque, the product of the speed and torque has to remain constant, because the total energy or power has to remain constant. Equivalently, you can get a higher torque by connecting the input to the red disc, the smaller disc, and taking the output from the shaft attached to the blue disc, right. This is exactly what was happening in the previous picture. We were taking the output from the larger from the shaft attached with the larger gear. So in that case the speed will decrease, but associated with the speed decrease we know that the torque has to increase, because that is what is dictated by conservation of energy. Okay, so the question is, if we have been able to attain this by simple friction disc, that is 2 discs with adequate friction, then why is it that we need to go for a gearing arrangement? That question is well taken. So let us understand how this arrangement basically works. Because it is a friction disc, the friction force develops only if there is a normal force between these two bodies. So the normal force at the point of contact has to be N, right. Only if there is a normal force, there is a question of friction, because friction is mu times normal force. So the mu times normal force is the tangential force or the frictional force which acts tangentially to these two discs, and because of this tangential force you have a torque which is mu times N times R1 on one disc and mu times N times R2 on disc 2, right. So therefore if you have to transfer a large torque, you therefore need a large N, right. You get to see that both the expressions for torque have embedded in it the value of N, which means that you need a large normal force which will permit, only a large normal force will permit the transmission of a large torque. Now that large normal force will eventually get transferred to the shaft which holds the gear, and that large normal force on that acting on that shaft will cause shaft deflection, and once the shaft which is carrying this disc deflects, that means the engagement will be lost. So therefore you cannot assume that the engagement between these two discs will be very reliable. Because of this large normal force, there will be shaft deflection, and once the shaft deflects, the gears mounted on these two shafts will no longer be in contact, and as such this is a deterrent for using friction disc. Friction disc can only be used if there is a requirement of very less torque being transmitted, only then friction disc can be used. The other important problem associated with friction disc is that the value of this factor mu is not very reliable. Again, it keeps changing depending upon conditions, depending upon lubrication conditions. So therefore it is not going to be a reliable design if you go by this friction disc, and therefore we come to gears rather than friction discs. So large torque transmission is not possible in friction disc. That is the major reason why we have to think beyond a friction disc arrangement, and the arrangement that we will talk about now is going to be the gear arrangement. Okay, so just a brief introduction to gears before we take a short break. That is, gears are toothed wheels. So instead of friction discs of this kind, what we will have in gears is that, and I'll show pictures for you. These gears will be wheels like these, but they will have some tooth, right. So gears will be toothed wheel, and the objective of a gearing system will be to transmit constant angular velocity ratio between the two rotating shafts at all times, right. This is very important. If the input speed, or rather if the input speed to the transmission, which is effectively the output speed of the engine, if the output crank speed of the engine is constant, the output of the transmission should also be constant. You should not have a gear system where the output of the gear system is basically a fluctuating speed output, even if the engine speed is constant, because a fluctuating output speed from the engine from the transmission side can be a very can have very detrimental effect, because that will really hamper the ride quality. For example, in automobiles, it will lead to large vibration and eventual failure. So it is very important that the gearing system does not introduce any additional fluctuations in the output speed. If the output speed coming from the engine is constant, gear should only be able to reduce it or increase it at by a constant factor without causing any fluctuations to this speed. So that is an objective, and we will see that this stringent because of this very stringent objective, you will have a requirement in terms of the profile of the tooth. The tooth profile cannot be arbitrary. For example, you will actually, though it may appear to you that these tooths are straight, in fact it is not so. The tooth profile is special geometry, and the requirement of this geometrical profile of the tooth stems from the fact that it is only a very specialized geometry which will actually ensure that the angular velocity ratio is constant between the two sides of the gear, the input side and the output side, that is. Okay. So that is a very crucial objective in our gearing system. As we will talk in greater details, but hopefully by now you have learnt some elementary concepts in mechanism. Gears happens to be higher pair mechanism. In contrast to your slider crank mechanism or 4-bar mechanism, which are lower pair mechanisms made of revolute joints or prismatic joints, gears are higher pair mechanisms. You will understand that a revolute joint or a prismatic joint has a surface of contact. When you have the piston moving within the cylinder walls, it is having a surface of contact between the cylinder walls and the outer cylindrical surface of the piston wall. So therefore, a slider crank mechanism is a lower pair mechanism, whereas a gear, the contact between two gears is, at least in a spur gear case, it is a line contact in 3 dimension, and if you take only the front view of it, as we will do in most of our illustration, we can say that it is a point contact. So none the same, gears are higher pair of mechanism. Even a helical gear will be a higher pair of mechanism. All gearing arrangement for that matter are higher pair of mechanism. Spur gears in particular will have line contact in reality. When you depict spur gears by a 2-dimensional drawing, you will have you depict only the front view of it, then you will get to see only a point contact, right. So point contact or line contact, either way it is a higher pair mechanism. So that way this mechanism differs from a lower pair mechanism which you have studied, which could be of mostly slider crank and the 4R mechanisms. Okay. The other important thing is that very rarely you use 1 or 2 gears, but we use a train of gears. Again, to get back to the transmission system of an automobile, there is not 1 or 2 gears, but quite a few gears. When you say there are 5, it is a 5-speed transmission, there are basically different gears that are there. So a collection of such gears will be called as gear trains. So as opposed to just 1 or 2 gears getting engaged, there will be a collection of gears, and as we will see, our transmission box is essentially a gear train. So we will study the transmission box as a gear train as we go along. Okay. So talking about different gear types, there are many different gear types. The one that we will study, that is associated with the transmission of motion between parallel shafts. You could have shafts in parallel, you could have shafts making an angle, you could have shafts which are skew, that means they are neither parallel nor intersecting. Accordingly, if you wish to transmit motion between any two of these different kinds of shafts, then you will have a different gearing arrangement. The ones that we are talking about, like in this case, in the case that we just talked about, here you see that these two shafts, the input shaft and the output shaft, are parallel. So therefore, we are talking about transmission between two parallel shafts, and the gears associated with the transmission of motion between two parallel shafts will be either spur gear or helical gear. Both of them will be fine for the transmission between two parallel shafts. So getting back to the point, that transmission between parallel shafts can be attained either through a straight tooth gear, which is called a spur gear, which is what we will study in greater detail. The smaller gear between the two gears, gearing, when we say that there is a gearing arrangement, there has to be two gears. The smaller gear is called the pinion and the larger gear will be called the wheel. Okay. But spur gears are not the only sort of gears which are possible for between two parallel shafts. You can also have a helical gear, and I will just talk about helical gear in a moment. But before that, there is another very interesting case where if we contemplate this situation, that one of these disc radius, one of the gear radius is actually going very large. As you know that if you have a circle of very large radius, it basically becomes a straight line, right. So in the limiting case that the wheel radius is becoming infinity, you have a special case of a rack and pinion arrangement. So in a rack and pinion arrangement, what happens is that you have a linear motion being converted to an angular motion. I can probably show you a picture to make myself clear. So this is a spur gear. As you can probably see that there are holes in this gear, and through these holes, and there is a keyway here also, if you could visualize this. So through these keyways and the hole, there is a shaft which will actually get attached with the gear, and once the shafts are attached to the two gears, basically the the gearing arrangement is such that motion from one shaft will get transmitted to the motion from the other shaft. But then since you see the alignment of the two holes are parallel, so basically the spur gear can only transmit motion in between two parallel shafts, it cannot do anything better. But now if you contemplate that this radius of this gear is keeping on increasing, but holding the radius of the smaller gear fixed, then you will have a situation of this kind, where this larger gear is now called a rack, right. So what happens when the wheel rotates? When the wheel rotates, it will be pushing the rack in one direction or the other. So the motion of the rack will be a linear motion, whereas the motion of the pinion will be that of an angular motion. So depending which side is the driver and which side is the driven, you will have the motion transmission as that of an angular to linear motion transmission situation. The other type of gear, as I was mentioning, is that of a helical gear. Please note the tooths of the spur gear are in alignment with the axis of the gear itself, right. The shaft axis and the tooth direction is along the same direction, right. Whereas in helical gear, you will see that the tooths are not exactly in alignment with the axis of the gear or the axis of the shaft. So there is a helix angle at which this tooth is cut. So that leads to a sort of quieter operations in gears. The dynamic loading is much better in case of helical gears as opposed to spur gears. Usually helical gears are more costly to make, but it is worth the cost in applications where customers are ready to pay that cost, especially some in high end cars where noise and vibration is an irritant. There it is, most of these gears will be helical gears. But in certain other applications, for example in lathe machine, possibly in the workshop conditions, we are not very worried about these additional vibrations, in which case we can tolerate the cheaper spur gear. But the point is, the only distinction between spur gear and helical gear is in the manner in which this tooth is cut. The geometry of the tooth, if you take it along any section, is going to be identical. If you just take a slice of this tooth as a section, then it is reasonably similar, I should say. But the point of distinction being that these tooths are cut along the direction oriented along the axis of the gear or the shaft itself, whereas these tooth on the helical gear are being cut at an angle or a helix angle as we call it. We are not going to study helical gears in any further details, but none the same you should appreciate that there are many different kinds of gears. Maybe in a later more advanced course on gear design you can study helical gears to more to a further depth. Another type of gear which is very important, again this is what is happening even in your differential of a vehicle, is that of a bevel gear. If you note carefully, these two gears are attached to some sort of a shaft or something which get probably attached to the shaft. So, the shafts are, or extended portions of the shafts would probably be these, right. So, as you can see that these shafts are intersecting, they are not parallel as in the case of spur gear. So, this gearing arrangement is called a bevel gear arrangement, right. Again bevel gear is something which we will not study in this talk, but if you can understand spur gears, then possibly you can take a more advanced course wherein you can get to know how helical gears and bevel gears are dealt with. So, these are the different types of gears. There are also a few more, that is you will have a worm gear arrangement and etc., but we are not going to talk about those arrangements. Maybe your design of machine elements course would talk about that. This is mostly about the kinematics of gears. Okay, I think this is the right time to take a pause. In case you have a question or anything to ask, I'll respond to you. Okay, GGIPG is asking that is the torque transmission of spur gear more than the helical gear? See, the question of how much torque is permissible in a spur gear as opposed to helical gear is a different question. The only the problem in spur gear in terms of transmission, as you will come to know when we talk about contact ratio, is that sometimes the contact between the pair of tooth is abrupt. Sometimes there will be one pair of teeth in contact, sometimes there will be two pair of teeth in contact. So, depending upon the load sharing capability, suddenly there will be an abrupt change that the tooth will see in terms of the load that it experiences. So, accordingly this leads to wear and tear of the gear tooth. In helical gear, due to the geometry of the tooth, the contact is gradual. Gradually the tooth come into contact and gradually the tooth goes off to the contact, right. So, in that sense the wear and tear associated with the helical gear tooth is much lesser than in a spur gear. So, if you presume that these two gears are made of the same kind of material, having the same kind of lubrication facilities, then one would expect that because of a smoother engagement process that typically happens in a gear, then the life of such gears are more. But the question of what the torque transmission of spur gear being more than a helical gear, you can transmit the same amount of torque, but the question is, if you do transmit the same amount of torque, then possibly the spur gear will have lesser longevity than the helical gear, because the contact is very erratic, so as to say, in spur gear, whereas the contact is smooth in helical gears, and as such the life of spur gear will be enhanced in comparison to the life of helical gear is more than in spur gear, because the contact is smoother. Okay, carrying on. What are torque and speed variations in case of planetary gears? Well, we have not yet come to planetary gears, but essentially the same idea goes through in planetary gears also. Even in planetary gears, it's finally a torque. I mean, there is an input, something is an input, something is an output. Whatever gear train arrangement that you give, it is finally going to scale up or down the speed and accordingly the torque. So, what we are going to do in the last part of the course, not today, but maybe 2 days down the line, we are going to analyze the speed ratios of different planetary gears. If you assume that the speed ratios get scaled with the power being held constant, if you get the speed ratios, you can also get the torque ratios, and that will give your desired answer. EPC is asking what are the application of bevel gears. As I said, one typical application of bevel gear is in the differential of your automotive, and the reason why it is used in a differential of an automotive is that when you have a vehicle and it has to take a turn, then one wheel has to move at a different speed as compared to the other wheel. So, from the same input you have to generate two outputs which are related in some way, but the two wheels cannot move at the same speed when the vehicle is taking a turn as opposed to when the vehicle is moving on a straight line. So, that can be attained using bevel gears. So, if you are interested, please read about differentials. If you or see some nice animations of how differential gear system works. So, in that you will see bevel gear application. IGCEP is asking, is there a limited value of torque ratio up to which spur gears can be used? Yes, if you want a very high torque ratio, you should go for a worm gear arrangement. Typically there will be limitations, but these limitations are dictated most from the material perspective. You know, if you have a good material or maybe a case hardened material where the gear tooths have been sufficiently surface treated and the wear and tear of the gear has been arrested, then you can carry on the spur gear even to a larger extent of torque. But you are right in saying that the torque ratio typically for our usual spur gears which are available will have a strict upper limit, and the limit of it arises from the failure perspective of the material. It does not arise from any kinematic perspective or any dynamic perspective, it arises from the perspective of the material erosion that takes place, because finally in a gear mechanism what is happening perpetually is that there is a rubbing between the two surfaces which are in contact, and if the surface treatment is not good enough in the gear material, then eventually this material will come off, this will get eroded, it will get worn out, and that is what will limit the torque ratio. Or if you actually put a very heavy torque, the tooth itself can break because it is not able to sustain that load. So, therefore, that is a requirement technically speaking, and you can get over that requirement in going for a better surface treatment or a better material. But yes, with the same material, if you wish to have a higher torque transmission, then you should not go for a spur gear, you should go for a worm gear will accommodate a much higher torque transmission. Okay, going to the next question, what are the applications of spur gear? Can we use bevel gear instead of spur gear? Bevel gear and spur gears are completely different applications. Bevel gears can be used only in case you are interested in transmitting motion between two intersecting shafts. Spur gears are used only in the case where you are interested in transmitting angular motion between two parallel shafts. So, the alignment of your shaft hopefully is fixed, in which case the type of gear that you should use in order to attain this transmission of motion characteristics will also be fixed. And to your first question, that what are the applications of spur gears? Spur gears are used, let us say in the lead box, if you see it's a spur gear arrangement. As I said, high end cars would mostly go for helical gears, but you will have in probably lower end cars and lower end vehicles you will have even spur gears. So, spur gears are used in certain kinds of automobile applications. Spur gears are usually the cheaper variants, helical gears are the more costly variants. Okay, another question, what are specific applications of helical gears over spur gears? Again, as I said, helical gears are used in automotive, I mean it is almost the same application, it is just that helical gears are having better what do I say, better transmission quality, better load bearing capacity as opposed to spur gears, but they are difficult to manufacture, they are more costly to manufacture. So, they are more costly variants of spur gears. So, it is as simple as this. So, if the application such as you are really looking for a high end car, then everything should be helical gears as opposed to spur gears. But if you are not ready to put in the additional investment associated with the manufacture of helical gears, then you may as well go for spur gears. Okay. So, that is the distinction in terms of helical gears and spur gears. Okay, JNTUA is asking, why do helical gears produce less noise than spur gears? Well, that depends upon the type of contact. If you look carefully, the contact between the spur gear tooths are abrupt, whereas the contact between helical gear tooths are continuous. It is not abruptly changing. As I said, when we come to contact ratio, we will realize that at times one pair of, for a case of spur gears, which is what we will talk, the contact ratio concept will elaborate to us that at times there is one pair of gear tooth which is in contact for a spur gear, and at times there are two pairs of gear tooth which are in contact. This essentially means that the load that is seen by the tooth is changing, or the distribution of the load is changing, and as a result this is causing some dynamic fluctuation, because this change is very abrupt. Suddenly from one tooth pair it will become two tooth pair. So this will lead to a very abrupt change in the load transmission characteristics between these two gear tooth. Such abrupt changes are not allowed in a helical gear tooth. If at all things change, the changes will be gradual, and as you know, if you hit a surface abruptly it will cause vibration and it will cause noise, whereas if I hit the surface continuously, I can apply the same amount of force, but if I apply it continuously it is not going to vibrate or produce noise, whereas if I apply the same amount of load, but if I apply it abruptly it will vibrate and produce noise. So as a result, with this analogy you can possibly visualize that helical gear tooths will be quieter in operation, and that is one of the USPs of helical gear tooth. Okay, someone is asking about normal force and tangential force in a friction disc. So what I'll do is I'll quickly explain that part. So as I talked about, in friction discs there are two friction discs in contact. Each of these friction discs are going to be mounted on some shaft, which is shown here. There will be a normal force obviously there between the two friction discs, because the two friction discs have to be in contact. If you just let it hang loose, then there is no normal force, then there is virtually no contact either. So these are the normal forces, and this is omega 1, which means the velocity of this point of contact is omega 1 r1, because this is r1, right. So to have a velocity of omega 2 r2 equals to omega 1 r1, so that means the omega 2 r2 should also be this way. So that means omega 2 has to be this way, right. So in other words, if the one of the friction disc is rotating in a counterclockwise fashion, the other will rotate in a clockwise fashion, right. And this is the kinematics of it, but let's talk about the free body diagram of this two friction disc. Already, as what is shown is that there are two forces which are the normal forces. What I will now indicate are the frictional forces. The frictional forces are definitely there, because that is what is causing the no slip condition. So if you look carefully, that the driver, I am taking this disc, the lower disc, as a driving disc. So this driving member is trying to move in this direction, which means there is a resistive torque mu n. Mu n is the friction force that is acting, which is trying to resist that motion. But because of the action reaction pair, there is a mu n that is going to get transmitted to the other member, that is mu n here, right. So if I draw the free body diagram of each of these discs, there is a normal force and there is a frictional force, there is a normal force and there is a frictional force. So this frictional force is basically going to give me the torque. So torque is mu n times r1 or r2, as the case may be, right. So the torque is basically mu n times r1 r2. This is what I said, and the point is that this normal force is going to eventually get transmitted to the shaft also, because the disc which is experiencing that force n is going to transmit that force back to the shaft. This is the free body diagram of the disc, not of the shaft. But now if the disc has to be in equilibrium, it has to get a force n from the shaft, which means the shaft has to get back the same force n, which essentially means that the shaft will be subjected, the shaft which is holding this disc will be subjected to a axial a transverse force n. So as you know that beams are very flexible structural elements, and this transverse force acting on a beam type of a structure, which is shaft in this case, will cause a shaft deflection. And once the shaft deflects, the gear which is sitting on the shaft will also sort of move from its position, and either it will interfere or it will lose contact, the gear or the friction disc, as the case may be. So shaft deflections associated with the shaft which is on which a transmission member is mounted is basically going to be having a very adverse effect on the transmission quality, and this is exactly what I have tried to elucidate in my talk. I hope that makes it clear for you. This, which gear is best for high pickup and which one for speed? See, I possibly don't get the question, but what you're asking is which one is the best gear. There is nothing like this is the best gear and this is the worst gear. Depending upon applications, you should choose the gear, and also you should have an eye on the economics of the situation. There is no point in having a very hi-fi gearbox and thus increasing the cost of your vehicle, whereas you know that your vehicle is going to be sold in a certain segment and it is not permissible to have such high costs. So, it don't go with what you think is the best, rather please use your good wisdom in understanding whether within the economics of the application should dictate whether you should really choose the best. Sometimes you know, depending upon the economics of the situation, you are supposed to choose a suboptimal technical solution. If so be it, that as I said, for a spur gear and a helical gear, the choice is basically dictated on economics, right. That is one factor. The other factor is, you know, when you are talking about shafts of different orientation, if you have, let us say, skewed shafts, that is shafts which are neither parallel nor intersecting, you cannot go for a spiral, you have to go for a different gear which is called a spiral gear, right. So, there are different kinds of gears in application. You cannot say this is the best gear and this is the worst gear. Depending upon what type of transmission you want, what is the cost associated with the transmission, you should choose what is the gear which is supposed to be used in that application. I hope I have made myself clear. Theoretical portion. So, now we will start our study on on spur gears. So, the first objective will be to dissect out the gear and to acquaint ourselves with the different terminologies associated with the nomenclature of spur gears. So, from here on we are only going to deal with spur gears. So, the most important geometrical term that will arise in our study of spur gears is that of a pitch circle. So, let us see what pitch circle implies. By the way, the figure here shows just a small portion of the gear. These are the tooth of the gear. The blank of the gear is not shown in its entirety. We are just showing a portion of it such that you are able to appreciate the different parts of a gear. As I said, pitch circle being the most important, we will take that head on. So, pitch circle of a gear is an imaginary circle. Please understand, there is nothing that you will be able to see on a gear which readily shows that this is the pitch circle. It is an imaginary circle on the gear which rolls without slipping on the pitch circle of a mating gear, transmitting identical motion as that of the mating gears. So, the point is that this is where all the discussion started, that you know things are already conceptually there in the friction disk idea. It is just that the friction disk is not a workable idea owing to the fact that the shaft will bend and eventually break also, and therefore, we had to contrive a different application which is what our toothed wheel application or a gear application suggested. But the point is that we somehow want to relate the motion transmission between gears to that of the case of the friction disk. So, the point is, even if we have engagement between a gear tooth pair, so let us take that there is two pair of there is a gear here and there is another gear here. Okay, I am just showing an instant where only one tooth is in contact, one tooth pair rather is in contact. We would like to replace this situation with that of a friction disk. So, we would like to think that whatever is the motion transmission that is happening in this case can be made equivalent to a motion transfer between two friction disks of this sort. So, we will try to contemplate that this motion transfer can that is achieved through this gearing arrangement can be equivalently attained by two friction discs which are shown in this fashion. So, the radius associated with each of these friction discs is what is said to be the pitch circle radius. So, associated with each gear, basically embedded in the idea of gear is the idea of friction disc. Whatever motion that the gear pair is transmitting, we would like to visualize that as an equivalent motion between the two friction discs, and the associated geometry of the friction disc will then become our pitch circle, right. So, therefore, pitch circle is an imaginary artifact which is sort of going to be very useful in terms of replacing the kinematics of a gear with that of a friction disc, because friction disc, the analysis is pretty simple. We would like to hold on to the simplicity of the analysis in friction disc, yet we would like to relieve or mitigate the engineering problems associated with friction disc. So, therefore, we are getting into gears, but the analysis we will always try to fall back on this idea of friction disc while we do the analysis, and therefore, we will get the analysis and the results out of it pretty simple, in a simple fashion. And to this end, to this idea that you wish to replace the gear with a friction disc, the concept of pitch circle arises. So, pitch circle is precisely that friction disc, because as was elaborated to you, friction disc essentially rolls without slipping on top of the other friction disc, such that the motion transmission does takes place. So, pitch circle is that precisely that friction disc. It is an imaginary circle which rolls without a slipping, as a friction disc should do, on the pitch circle of the other mating gear, such that the transmission is identical in both the cases. Okay. So, that is the definition of pitch circle, and I hope you got the concept clear, because pitch circle will be referenced very frequently. Pitch circle, the entire geometry of the gear is based on the pitch circle. Okay. So, let us now once again look back to how the motion transmission of the gears do happen. With this analogy, where we are saying that the motion transmission between gears is identical to motion transmission between two friction discs with diameters equal to pitch circle diameter. So, we have contrived this pitch circle business simply to replace the concept of motion transmission of gears to a concept of friction disc, and we pretty well know how to do the motion transmission for friction disc, because that was omega 1 r1 equals to omega 2 r2. So, here too we will get the same relation, but remember r1 r2 are the pitch circle radius, r1 r2 are not any arbitrary radius which you may measure looking at the gear, right. So, that is the point that comes, but before we do that, please note that the point of contact of these two circles is having a technical name, that is called the pitch point. So, the equivalent pitch circle or the friction disc, if you would like to call them, they will meet at only one point, because friction disc by the very nature of its operation should be meeting at one point. It cannot be a surface contact, it can be only a point contact in the front view. In the 3-dimensional, it is obviously a line contact, but in either case it is a higher pair of mechanisms. So, therefore, there has to be only a point contact in the front view, as is depicted in this illustration. So, this point contact between the two friction discs, or equivalently the pitch circle, is called the pitch point. So, the two discs roll without slipping at the point of contact. They will have the same velocity as we have explained in the case of friction disc, and that essentially leads to this very important result, that omega 1 r1 is equals to omega 2 r2 even for a gear, right. But please note, this radius, when we are talking in the perspective of gears, this radius is something actually which you cannot take a scale and measure it. It is not even visible. That is why we say it is an imaginary circle, but it is there in the design of the gears, that everything is referenced with respect to this geometrical parameter, which is called pitch circle radius. So, we have got back the same kinematic result that we had even for our simpler case of friction disc, omega 1 r1 is equals to omega 2 r2. But please note that a gear transmission system is a positive drive system as opposed to a friction disc system. What I mean by positive drive system is that one member is pushing the other member to move, whereas in a friction disc case the principle of operation was based on the fact that it is a no slip condition. The friction is sort of tying the two members together and is ensuring that there is no relative motion possible between the two members. So, the physics of the motion transmission is completely different between the friction disc and the gear. However, the mathematics turns out to be equivalent, that is, in both cases we have omega 1 r1 is equals to omega 2 r2. Okay. So, that is about motion transmission of between gears, which is with reference to the pitch circle, not any other circle. Now, we will get to see many more other different kinds of circle in the gears, and actually some of them are easily discernible when you see the gear. For example, if you could very well contemplate that there is a circle passing through the outer periphery of the gears, and this circle, which obviously is not drawn. So, therefore, we still say that it is an imaginary circle, but it can be visualized with very little effort, that a circle which just passes through the outer periphery of the gear will be called as addendum circle, right. And addendum itself is the radial distance between the pitch circle and the addendum circle. So, the addendum circle is here, pitch circle is here, and the radial distance between the two is the addendum. Okay. So, that is the nomenclature for you. The dedendum circle is the circle which is passing through the innermost region of the tooth, or the base of the tooth, if you may say, but the technical word base circle rather is reserved for something else. So, it is a it is a circle which is passing through the bottom of the tooth, just like the addendum is passing through the outer periphery or the top of the tooth. The dedendum circle, as is illustrated in this drawing, is an imaginary circle which is passing through the bottom of all of these tooth, and therefore, similarly you can define dedendum to be the radial distance between the dedendum circle radius and the the radial distance between the dedendum circle and the pitch circle. So, this is the dedendum circle, which is marked here, and this is the pitch circle. So, therefore, this distance is the dedendum. Okay. Carrying on, face width. Face width is the portion of the gear which you see in the side view. This is the front view of it, this is the side view of it. So, in the side view, this area that this width that you see is the face width. So, the thickness of the gear along the axis is called the face width. Remember, the tooths are cut out such that the tooth is parallel to the axis of the gear itself, right, because this is a spur gear. Had it been a helical gear, this would not have been true. So, for the face width is the dimension along this depth direction of the tooth. So, this is what is called face width. The portion of this surface which is above the pitch circle is called face, and the portion of the surface which is below the pitch circle is called the flank. Remember, the contact between the two gears will take place along this surface. So, all sorts of surface treatment should be done on this surface, because this is what will be prone to the rubbing action once the contact takes place. So, this is very important in terms of manufacturing reliable gears, gears which have long life. You should do the surface treatment on the face and flank of the gear. On this portion, which is called the top land of the gear, you do not need any surface treatment, because there is no rubbing action that is going to happen in the top land or even in the bottom land. It is only going to be the face and flank which will be prone to a lot of surface related failures, and as a manufacturer of gears, you will do well to enhance the surface characteristics of these gears, surface characteristics of this region. So, technically the surface over which the contact between the two engaging tooth take place is the face and the flank. The face is the portion which is above the pitch circle, flank is the portion which is below the pitch circle as depicted in this drawing. Top land and bottom land. Top land is the area at the top edge of the tooth. This is the top edge of the tooth, the one which is passing through the addendum. Now, if you go along the depth direction of the gear, the area that is recovered is going to be the top land. Similarly, the bottom land is the flat land that you see at the base of the tooth, that which is corresponding to the dedendum. So, that is called the bottom land. So, area at the bottom edge of the tooth along the direction of thickness will be called the bottom land. But please remember, top land and bottom land, there is absolutely no contact between the engaging gear tooth that is taking place. The contact between the engaging gear tooth will take place in this surface or the other surface, depending upon what becomes driver and the driven. So, usually these faces and flanks of the gears will go through a, I mean, there is a requirement that there has to be a good surface quality of these portions. If surface quality need not be achieved in the top land and bottom land owing to this application requirement. Okay, coming to the next terminology, circular thickness. So, circular thickness is the thickness of the gear tooth measured along the pitch circle. You may see that at the addendum region the tooth thickness is smaller, whereas at the dedendum thickness the tooth thickness is wider. So, when we wish to refer to what is the thickness of the tooth, we cannot quote a single value, because the thickness of the tooth is changing as one goes from dedendum to addendum. It is decreasing as it goes from dedendum to addendum. So, therefore, as I said, most of the geometry will be with reference to the pitch circle. So, when we quote the value of thickness of a gear, it is technically termed as circular thickness, because it is the thickness measured along the pitch circle, because pitch circle is the most important geometrical reference point in our study of spur gears. So, here we see that the pitch circle, if we travel along the pitch circle, if we take a string and along the string, if we measure using this string along the pitch circle, if we measure the thickness, then this thickness will be referred to as the circular thickness of the gear. So, thickness of the gear tooth measured along the pitch circle is the circular thickness. So, that would be given by this, it is not referred to in this circle, in this illustration as I see it. Maybe tooth thickness, what is referred to is basically the circular thickness, that is right. So, this label tooth thickness, which is the thickness along the pitch circle, is the equivalently the circular thickness. I have taken this picture from Norton's book. So, Norton refers this to as tooth thickness, it is equivalently called circular thickness. Okay. Next is space width. So, just like we measured the thickness of the solid portion of the teeth, we would like to have a measure of the extent of the gap between the two teeth, right. So, that is technically called as space width. That is if we try to measure the distance between these 2 points on the pitch circle, obviously the width is different at the addendum and at the dedendum. At dedendum, the width between the gap between the two teeth is less, the gap between the two teeth is widest at the addendum level. But if we wish to refer to a single geometrical parameter which sort of gives a feel of what is the space width, that should be with reference to the pitch circle. So, accordingly space width is defined to be the distance between two consecutive gear tooths measured along the pitch circle. So, as I said, it is always that the geometry is referenced with respect to the pitch circle. You will note that it is within this space width that the teeth from the other meshing gear will come and sit, such that the engagement takes place. So, to ensure that there is no interference, or rather there is adequate space for the corresponding gear tooth for another gear to come and sit in this space and hence have the engagement with this gear, usually space width will be larger than the circular thickness, which means the amount of gap that is left is larger than the amount of solid material that is there at the pitch circle level, because you do not expect that the teeth will get completely inside, but it should get in at least to the level of the pitch circle. So, once you have a teeth which is going inside this gap, you will have a good engagement. You cannot have a situation where the thickness is greater than the width, in which case the tooth will not be able to get in, it will actually have interference readily. But interference in the terminology of gears means slightly different thing, we will come to it in a moment. But you can understand that to permit a smooth engagement, you need to have space width to be at least same as circular thickness, but in fact more gap is left, and this gap, the difference between space width and circular thickness, is actually referred to as backlash. This backlash can be a great nuisance in certain applications. Let us say in certain applications, if you wish to reverse the motion of the gear. So, let us say this gear drive is actually used to rotate a radar, as the radar is tracking a military aircraft vehicle, right. So, if the radar has to continuously track the motion of a certain aircraft which is doing very strange maneuvers, and the gear essentially controls the motion of the radar. So, in such situations, it may be necessary to have a reversible gear, that is, the driver gear may rotate in one direction and also the other direction, depending upon how the radar wishes to change its course, which again depends upon the motion of the military aircraft. So, if the driver gear wishes to reverse its direction, then you can understand when it reverses, the driver gear will have to traverse a distance which is equal to a backlash without actually driving the driven gear. So, within this small time, this when the driver gear is traversing through this backlash, there will be actually a no load condition for the driver gear, and the driver will actually not drive the load, which is the radar weight in this case, I mean the motion of the radar being the load. So, in such a case you are going to have a backlash. So, the controller will say that the driver gear has been rotated, but even the when the driver gear, even if the driver gear has been rotated by the controller, it will not affect any actual motion, because it is moving through the backlash region, wherein the driven gear is not rotating, and therefore there is no motion transmission to the radar. So, this backlash can be of very detrimental consequences, but in a more sort of civil application, like as you have in automobile cases, backlash need not have that bad effect. We can live with a little bit of backlash, especially in terms of longevity, because we would like to keep a little bit of backlash to make sure that the gear tooth has a very perfect engagement without any adverse effect in terms of wear and tear. So, in terms of longevity, this backlash is a good thing. That is why I said, depending upon application, certain thing may be good or bad. So, backlash is good in terms of longevity, backlash is not good in case of military applications, where tracking with an accuracy becomes the sole criteria. Okay. So, carrying on with other terms and terminologies, the next term we encountered is that of a circular pitch. So, circular pitch is the distance along the pitch circle between two identical points. So, consider this point right at the center of this tooth, and for a successive tooth, if you take another identical point, then the distance between these two measured not along the straight line, but along the pitch circle again is going to be the circular pitch. So, circular pitch is the distance along the pitch circle of two identical points on successive tooth, right. So, these are the two successive or consecutive tooths, you pick up two identical points, measure its distance, that becomes the circular pitch. So, as you know, the total circumference measured on the pitch circle is pi times dp, dp being the diameter of the pitch, and if there are n number of tooth on the gear, that means there are n number of segments on this circumference on the pitch circle. So, therefore, the pitch circle the circular pitch would be the pitch circle circumference divided by the number of tooth. So, PC, which is the circular pitch or the circumference of the pitch circle divided by the number of teeth, is going to be pi dp by n. So, this ratio dp by n is going to be very important. Pi times dp by n is referred to as circular pitch, and n by dp, the inverse of dp by n is called as diametral pitch, and dp by n is called module. So, in other words, circular pitch is module times pi, right, and diametral pitch is reciprocal of module. So, these three quantities are very related, module, circular pitch and diametral pitch. Different standardizations exist in terms of which the different gear dimensions are standardized. So, gear dimensions will be usually standardized with respect to the module or the diametral pitch, depending upon which conventions you look at. There are BIS conventions, AGMA conventions, and so on and so forth. I will show some of those conventions to you in possibly the next class, but the crucial point at this stage to take home is that these three concepts, module, diametral pitch and circular pitch, are all interrelated, and it will turn out that all these other parameters like addendum, dedendum, tooth thickness, all of these will be referenced with respect to these quantities. Okay. So, when they sell gears, they usually have it referred that this is the module of the gear and this is the pressure angle. With it comes in standard sets of module and standard sets of pressure angle. Once you know the module and the pressure angle and you are knowing which standards you are using, then you can recover all these dimensions in using the formulas that are available in such standards, and I will quote one of them as we go along. So, that makes it very imperative to understand the concept of these interrelated concepts, basically diametral pitch, module and circular pitch. So, as I said, as per the standardization, geometric dimensions of the gear is given in terms of module or diametral pitch, and it is important that the machine gears, two gears which have to engage with each other, they must have these parameters to be identical between the two gear tooth. And there is a reason why, you know, the engaging gear tooth has to have the same module or the same circular pitch. The reason is just geometrical, nothing else, just driven by kinematic consideration, which is what I am going to show to you. So, please remember that module is d by n and diametral pitch is the reciprocal of it, and the circular pitch is pi times module. All of these ratios between the two engaging teeth, between the two engaging gears must be same, and the reason why it has to be same is driven by a kinematic consideration, as is shown in this slide. So, the what I have shown here is two time instants when a pair of gear tooth is in contact. So, at time t equals to 0, we have this picture where the red pair of tooth is in contact, and at a later time instant the engagement has changed. So, the red pair of tooth has now lost its contact and the contact has now come in the blue pair of tooth, right. So, the red pair of tooth has gone this way, and it's the blue pair of tooth now which has been in contact. So, the successive tooth has now taken its place. So, this is what is happening after a later time instant delta, right. So, after a delta time, the blue tooth pair has now come in contact. So, this tooth has come here, this tooth has come here, this blue tooth has now taken the position of this red tooth, this blue tooth has now taken the position of this red tooth. So, basically what has happened between these two time instant is that this blue tooth has taken the position of this red tooth, which is what you see in this diagram, and this blue tooth has taken the position of this red tooth, right. And what follows is a green tooth which will eventually take the position of this blue tooth in the next time instant, which is not shown, right, because this is enough for our analysis. So, what we realize is that after a certain lapse of time, it is a succeeding tooth which will take the position of the tooths which are presently in contact, right. So, in other words, what that means is the following, that is the time taken by this blue tooth to occupy the position of this red tooth must be exactly the same as the time taken by this blue tooth to occupy the position of this red tooth. So, this is what we will try to find, what is the time taken to analyze for each of these tooth to occupy the position of its tooth which is lying ahead of this tooth, right. So, accordingly we will firstly compute what is the distance traversed by these two blue tooths such that it is able to take the place of the red tooth at t equals to 0, and that distance divided by speed will give the time, and if we know that the time has to be exactly matching, then we will get our conditions that we are looking for. So that the angle of between two successive tooth in any gear will be given by 2 pi divided by the number of teeth, because the total angle over the entire gear is 2 pi, and if you know the number of teeth to be n, then the angle between any two gears will be the angle between any two successive tooth in a gear will be 2 pi by n. Accordingly, for gear 1, the angle between the blue tooth and the red tooth which are at successive positions will be 2 pi by n1, n1 being the number of gear of tooths in gear 1. Similarly, the angle between the successive tooths in gear 2 will be 2 pi by n2, n2 being the number of tooth in gear 2, right. So, theta 1 is 2 pi by n1 and theta 2 is 2 pi by n2. So, the time interval by which this gear 2 is or this tooth in gear 2, blue tooth in gear 2 is occupying the position of the red tooth in gear 2 has to be exactly the same as the time interval at which this blue tooth in gear 1 occupies the position of this red tooth in gear 1. Based on this consideration, what is the time taken for this blue tooth to cross a distance of theta 1, that is theta 1 divided by omega 1, and theta 1 has been evaluated to be 2 pi by n1. So, therefore, the time required for this blue tooth to come and sit in the position of this red tooth is going to be 2 pi by n1 omega 1. Similarly, the time taken by this blue tooth to come and sit in the position of this red tooth, that is at the level of gear 2, will be theta 2 divided by omega 2. Theta 2 has already been found as 2 pi by n2. So, therefore, we will have 2 pi by n2 omega 2 as a time taken for this blue tooth to come and sit in the place of this red tooth. But as we know, as we have argued rather, that the time taken for each of these tooth sitting on two different gears must be exactly the same, only then the picture will completely repeat after every engagement. So, therefore, we must have these two quantities to be exactly the same, and this essentially means that the number of tooth is inversely proportional to the rotating speed. What we have also figured out from the kinematic considerations, from the no slip conditions, from the analogy of friction disk, is that the rotational speed bears an inverse proportionality even with the size of the gears. So, we have also seen R1 omega 1 equals to R2 omega 2. Now, what we are seeing presently is N1 omega 1 is equal to N2 omega 2. So, both the tooth thickness, both the number of tooth as well as the size of the gear are in inverse proportionality with the speed of the gear. So, as such, the speed of the gear and the number of tooth are directly proportional, which means R1 by N1 must be equals to R2 by N2, and as you know, that effectively means the diameter by the number of tooth are got to be same, that ratio of diameter by the number of tooth have got to be the same between any two engaging gears. If this condition is not met, the engagement will not happen, because engagement, if at all it happens, it has to be identical between the tooth pair which is coming in contact. You cannot have a completely different sort of engagement that is happening between the different tooth pairs. So, therefore, to have identical engagement, this condition is a must, that the ratio of diameter to the number of teeth must be exactly be the same for both the gears that is under engagement, and that effectively means that the module, the circular pitch, the diametral pitch, all of these things have to be the same. Diametral pitch, module, circular pitch between two engaging gears must be the same. This is the requirement that we were talking about few minutes earlier. Okay, going ahead now, the next concept, I will just like to revisit elementary concepts of mechanism, just to give you an idea about or rather just to revive the idea of what is a higher pair mechanism. So, higher pair mechanism, because we understand our gears are higher pair mechanism, let us just look back as to what a higher pair mechanism means. So, here what I have shown in the schematic illustration is that there is a blue body and there is a red body, and there is just a point contact in the front view of it. If you consider these bodies to be 3 dimensional, essentially there is a line contact. What has not been shown is the side view of it. If you consider the side view, you can take it to be a line contact. In the front view, there is a point contact. So, okay, in general, for a 3 dimensional bodies of this sort, you will get to see a line contact. Such contacts, when mechanisms finally are interconnected bodies. When these interconnected bodies have line contact, we call them higher pair mechanism. When these interconnected bodies have surface contact, we call them lower pair mechanism, as you get to see a pin joint. When you have a pin joint, then basically it is the entire area, outer area of the pin, which is sort of forming the area of contact between the two interconnecting members. So, pin joints are therefore lower pair mechanisms, or pin jointed links form a lower pair mechanism, whereas higher pair mechanisms will have only line contact or point contact. Now, what is so special about higher pair mechanisms? As you can understand from this illustration, if I hold the blue body fixed, there is two possible motions that I can give to the red body. That is, I can undergo a curvilinear translation on this blue body. Contemplate the blue body to be fixed, in which case you can have either a curvilinear translation of the red body. So, it can just translate on this surface of the red body, or like a wheel does, it can have a no slip condition maintained at the point of contact, and it can rotate about this point of contact. So, these two motions are completely distinct and therefore, we get to infer that the higher pair mechanism is essentially a 2 degree of freedom system, the 2 degrees of freedom being relative translation as well as relative rotation. Please note that the lower pair mechanisms that possibly you have studied, the revolute joint and the prismatic pair, are all 1 degree of freedom, they allow only 1 degree of freedom. So, for example, in a prismatic joint only translation is allowed, in a revolute joint only a rotational motion is allowed, whereas in this sort of a higher pair mechanism both are allowed, and that is one of the characteristics of these higher pair mechanisms. The instantaneous center, if you recall what is instantaneous center, instantaneous center is a point on this you could mark a point such that the instantaneous center, whether it is embedded in body 1 or body 2, will have the same kinematics, will have the same velocity, I am sorry, not the same kinematics, it will have the same velocity. So, we are talking about instantaneous center of velocities. So, the deal that we wish to ascertain now is what is the instantaneous center of a higher pair mechanism. So, instantaneous center by its very definition means it is a point embedded in both the bodies, such that whether you consider this point to be embedded in body 1 or you consider this point to be embedded in body 2, either way it has the same velocity. So, you have to find that instantaneous center now between these two higher bodies which form a higher pair mechanism. But then you realize that when the bodies are forming a higher pair mechanism, there can be two possible relative motion, either of curvilinear translation or that of relative rotation about the point of contact. If it is relative rotation about the point of contact, then as I said, then practically the point of contact is under a no slip condition. It is just like a wheel which is gripping the surface. So, both the point of contact, whether you assume it to be the point on the blue body or in the red body, either way it has 0 velocity. So, the point of contact essentially becomes your instantaneous center. So, in dealing with the relative rotation or rolling without slipping condition, the point of contact is the instantaneous center. It is different in the case of relative translation. In relative translation, since this body is undergoing curvilinear translation on a curvilinear path, the center of curvature of the curvilinear path is essentially the instantaneous center, because you can replace this as a higher as a lower pair mechanism, and once you replace this as a lower pair mechanism, it is easy to understand that the revolute joint of this lower pair mechanism is going to be essentially the instantaneous center. So, using all that analogy, you would have looked at your elementary kinematics discourse, that there are two types of instantaneous center that are possible in a higher pair mechanism. Now, these two cases are actually the extreme cases. You can have a mixture of both. You could have relative translation also embedded along with the relative rotation or rolling without slipping. So, in which case the instantaneous center could also be, the position will be changing. But these two are being the extreme cases, it is easy to figure out the instantaneous centers in these two cases to be, one, in the case of relative sliding it falls to be on the center of curvature of the path. In case of rolling without slipping it falls exactly at the point of contact. Please note that in both the cases the instantaneous center is actually passing through the common normal between these two bodies. So, obviously the point of contact passes through the common normal. Also the instantaneous center, which is the center of curvature in this case, the center of curvature also passes through the common normal in this case. This is true for any body, not just bodies which are shown on in this fashion in the circular, what looks like circles is actually true for any body, not just circularly shaped objects. That is because any arbitrarily shaped object can be approximated in an infinitesimal sense as a circular shaped object. So, using all these concepts we arrive at a very crucial result, which says that the instantaneous center between the higher pair lies along the common normal between the interconnecting bodies which form the higher pair. So, here we have these two bodies which are forming the higher pair. So, we can be dead assured that whatever be the relative motion, whether it is rolling without slipping as in this case, or it is the case of relative translation, or it is a case of a mixture of these two motions, in any condition it will, or it is assured that the instantaneous center will be along the common normal. But the point is, where exactly on the common normal it will fall, that is not assured. If it is at the if the kinematics is such that it is only relative sliding, it will be at the center of curvature, that can be pinpointed. If the kinematics is such that rolling without slipping is the type of motion that we are getting, in which case the point of contact is the instantaneous center. So, again it can be pinpointed. But in general the motion can be a combination of these two motion, which is why the instantaneous centers cannot be determined in a pinpoint fashion. We cannot exactly locate on the exact location of the instantaneous center between two general higher pair of two general bodies forming a higher pair mechanism. So, that being said, we will understand that instantaneous center none the same will lie along the common normal. The exact location on the common normal where it is located, that will be determined only if we know something more about the motion itself. But we will see, and in the next slide possibly, that there are ways in which we could determine, one of them being Arnold-Kennedy theorem. But at this stage we only appealing to the basic kinematic arguments, we can only say that the instantaneous center of the higher pair mechanism can lie anywhere along the common normal. Where it lies cannot be determined through this argument at least. And all this is pertinent because gear tooth in mesh will form a higher pairs. So, we will see how to determine instantaneous centers for a gear tooth pair, and that will eventually lead to what is known as fundamental law of gearing. This is the basic premise based on which the geometry of gear tooth will get determined. So, we will take that part up possibly in the next class because it is a conceptual topic, but we will start from here, that we, with this basic background of the gear geometry and the terminologies associated with it, and with a basic understanding of the instantaneous center concept of mechanisms, especially that in higher pair, our next milestone will be to determine the instantaneous center for a gear pair which is in engagement, because finally this gear pair will form a higher pair mechanism, and from there on it will lead us to what is known as the fundamental law of gearing. So, that will be taken up in the next lecture. At present I would like to stop here, and if there are any questions or clarifications based on today's lecture material, I would be happy to resolve them for you. GJB is asking, is the gears more powerful than a hydraulic arm? See, there's nothing like less power or more power. The power is coming from an engine. The power is never comes from the transmission. So if your question is the gear able to transmit as much power as a hydraulic mechanism, that question is well taken. But there is nothing like gear power. The gear doesn't have any power because the engine delivers the power, the gear simply transmits the power, but in the transmission process it does play with the torque speed ratios. That is the objective of the gear. Gear is not a powerful or less powerful machine element, right. But if you are looking for very high transmissions at low speed, then hydraulics is the solution. If you are looking for high speed transmission, then hydraulics will not do it for you. Hydraulics will have some lag. Then you should go for a mechanical transmission, and gears are essentially mechanical transmission. SUCCET is asking me what level of backlash is acceptable. That is again dictated by application. If it is in my car, I don't mind a little bit of backlash. It may give me some vibration at the most, but I may not feel it also, right. But if it is a military application, it is dictated by how much is the tolerance levels of your application. So I cannot quote a number saying that this much backlash is applicable. Okay, BEC is asking what is pressure angle. That will be covered in tomorrow's lecture. I would not like to be dwelling on that right now. What is the role of module of a gear in power transmission? Module of a gear is an important concept in terms of standardization. All the gear geometries are getting reference. I can possibly show you the result. Okay, I think in one of my later slides I would have these gear geometries being standardized. Yeah, so this is these are the standard dimensions of a typical gear. So as you see, the M here stands for module. It is not meter, right? So the addendum, dedendum, working depth, hole depth, circular tool thickness, and many other parameters of the gears, all of these will be referenced with respect to module. So essentially what the gear manufacturer will say is that he is selling gears of a certain module, let us say 2.5 module. Once he says that to you, and he will also say the pressure angle and the module are possibly the only things which you need to know. Everything else can be calculated based on such standard formulas. This is based on the SI standards, there are ACMA standards, there are BIS standards. Each of these standards have different variants of these formulas, but if you know which standard the gear has been manufactured as per which standard, if you know the pressure angle, if you know the module, then you can work out all the geometric details of the gear that you are seeing on the shelf, and therefore it is very important in referencing the gear. So that is the application of module for one thing. GGIPG is saying why gears are circular above the pitch circle only at the face. I'm sorry, I didn't understand your question. Gear, we are talking about circular gears. There are non-circular gears also possible, but we are not talking about non-circular gears, at least in this course. Circular gears is what is interesting to us because circular gears will give us constant angular velocity ratio. I don't get to see the point that what you meant by saying that this is circulars only above pitch circle. See, if I can show you geometry once more, gears something like this. Yeah, so gears, spur gear or helical gear, each of them, if you take a section of it, it is a circular. So gears are circular, at least the ones that we are talking about, the gears are circular. I really didn't understand what's your confusion regarding circularity of gears. Maybe you can talk about it. If you hand raise, we can clarify it. Okay, there is a question from RITSDS. What is instantaneous center actually? Looks like you have not come across this concept, which is usually taught in the first part of the mechanisms course. So look back at my lectures. the video of it will be posted, but just to be brief, instantaneous center is a concept between two interconnected bodies. Finally, you must understand any mechanism is a group of interconnected bodies. If you take any two interconnected bodies, the question is there any point that you can identify which has identical velocity, whether you consider that point to be embedded in body 1 or body 2. If you can find that point is the instantaneous center, right. There are ways of finding instantaneous center. Usually we do it for lower pair mechanisms, but I am doing the proportion that I am dealing with is about finding instantaneous centers for higher pair mechanisms. You will do well to look at any book in mechanisms. If you are not comfortable with it, just read up the first part. It will have the concept of instantaneous center explained. If you want further help, talk to me. Hopefully after the class we can have a discussion about instantaneous center. Okay, SVC is asking, is lower pair observed in mechanism of gears? Actually the interconnection between the shaft and the gear is a lower pair. The interconnection between the two gears is a higher pair. So in that way, if you call that there is a revolute joint basically, which is the interconnection between the shaft and the gear. So in such a fashion, you can argue that there is a lower pair sitting in the transmission box. But what I was referring to is the engagement between the two gears itself. I was not referring to the contact between the shaft and the gear. So in this respect, I was qualifying the engagement between two gears to be that of a higher pair mechanism. Okay, is height of tooth of one small gear the same as height of tooth of bigger gear despite the difference of radius of gears? Yeah, you are talking, the GGIPG is talking about the tooth height possibly. So all of these are referenced in the standard tables, and as you will see that these standard tables are all referenced with respect to module, right. So all the geometries will be with respect to the module. So between any two meshing tooth you will have the module to be fixed, right. So if the module is known, as I said, every other geometrical dimension can be recovered, and these formulas will give you those geometrical dimension. So this is something that you will learn when you come to gear design probably. This is not a course in gear design, this is about kinematics of gear. How does the motion transfer between the two gears take place is the most important objective that we have in our present study, but I do not mind taking a few questions on gear design also in case you have a natural interest towards that topic. Okay. Going to the next question is, how will the affect the power transmission if the circular thickness of the tooth of the gear is increased? Explain in context to faced with. See, all these dimensions are referenced basically from the strength criteria of the gear, because finally what will happen is that the gear tooth will have to take the load, and when it takes the load which is greater than what it can endure, it will undergo failure. So what the gear designers will do is, with extensive experimentation, they will figure out that what is the maximum load that can be endured by a certain dimension of the gear. Accordingly, they will figure out what are the dimensions that is required in order to transmit a power. But in this discussion, which is about kinematics of gears, we are basically concerned about, we are basically assuming that the gear is a rigid body. We are not worried about the flexibility of the gear tooth. Remember, stresses and strains arise because of the flexible or compliance of the structural system. It does not arise if the structural system is assumed to be rigid. Failure does not arise if the question of failure henceforth is therefore is not apparent in the study of rigid body dynamics. Here, when we are talking about kinematics of gears, we are taking basically the perspective that we are taking is that the gear is a kinematically rigid object, and we are looking at how to design the, let us say, the tooth of the gear such that we attain a constant angular velocity ratio. That is our primary motive. But I take your question that what are the factors that go behind in the calculation of the exact geometrical details of these gears, these gear tooths. The factors which go behind in the calculation of these numbers is the numbers that you see on your slide. are basically the strength calculations. So, there are FEM calculations possible, there are experiments possible based on which they arrive at what is the acceptable values of face width, of tooth thickness and so on and so forth, such that the tooth will not fail during its operation. The next question is, what is the significance of friction between geared tooth? See, as I said, as opposed to a friction disc which works on the principle of friction, the principle of operation of a gear does not depend upon friction. It is a positive drive system. Positive drive system means one element or one member is pushing the other member, because it is one tooth which is pushing the other tooth, and that causes motion and torque transfer, right. So, friction typically is not required. So, therefore, you should have well lubricated gears, whereas it is the other way around. In case of friction disc, you should the friction disc will work only if there is friction. If you make friction disc which are having a supernatural finish and which are very well lubricated, essentially you are bringing down the friction, and then it will not be able to transfer torques at least to a high level, right. So, therefore, that was the reason why we shifted to gears as opposed to the academic concept of friction disc. So, the significance of friction is absolutely not there in the operation of gears, but practically speaking there is friction. You cannot reduce friction to 0, and when these gears are in engagement, because of friction there is loss of energy, there is a transmission efficiency concept, but transmissions have known to be much more efficient than especially the mechanical transmission is much more efficient than the engine itself, whereas the engine efficiency is of the order of 40%, 50%, I am talking about the thermal efficiency, but transmission efficiency can go up to 95%. So, therefore, usually friction can be controlled by a well lubricated engine, but it cannot be killed completely, and whatever friction remains is going to be a drain to the power requirement, to the power calculation. It is going to be a power loss. So, you will do well to have a well lubricated transmission system which sort of does away with the frictions that is there between the mating gear tooths. VC is talking about redundant degree of freedom. The redundant degree of freedom concept does not arise in case of gears, it arises in mechanisms. So, this 6-hour talk is not about mechanism, this talk is about gears. So, I will refrain from giving you talking about redundant degrees of freedom. Redundant degrees of freedom does not arise, at least in spur gear context. So, no point in talking about that. Okay, how does the number of teeth on gear affect the transmission of motion? The number of teeth in a gear affects contact ratio, it affects the interference aspects. So, the number of teeth, if the question that you had in mind is that if we could do it with, let us say, a very less number of teeth, why manufacture a gear with so many teeth? But then if you have a gear with very few number of teeth, as will be shown, there will be a chance of interference. So, therefore, you must have adequate number of teeth. What we will do hopefully in the next class is that we will find out a criteria which determines the minimum number of tooth to avoid interference. So, therefore, if any number of tooth which is beyond that critical limit is going to be good enough for our working purpose. The other issues that are there in the selection of number of tooth, these are all gear design questions basically, these are not kinematics of gear question, but none the same I am taking it. So, the other factor which goes behind the selection of number of tooth is, let us say, contact ratio. So, contact ratio essentially determines how many pair of gear tooth is in contact. If there are more number of tooth pair that is in contact, then there essentially the load is getting shared by so many number of tooths rather than just a one pair of tooth. So, that actually implies that there is less stress that is developed on the gear tooth, and therefore, the gear tooth can have possibly a longer life. But there is more to it than meets the eye. So, high contact ratio gears have their own problem. So, all that I wish to say is that the manner in which these details are fixed is a matter of gear design, and most of these things have been settled by long periods of study, and therefore standardizations of the kind that you see on your slide at this moment has been arrived at. But this course is not about gear design, this course is about uh, understanding the motion transfer characteristics of a gear, assuming them to be completely rigid. Just like in engineering mechanics and mechanisms course, you assume that the bodies of your interest are completely rigid and they do not have any stress considerations, at least in the course. Therefore, and the analysis proceeds with that basic assumption. We will have a similar perspective for the study of gears also, but yes, the question is well taken that stresses do arise in practical application, and we, based on the amount of stresses which are getting induced during the actual operational condition, the dimensions are determined. But such stress calculations for a gear tooth is too far fetched to be done in this course. You will need a more advanced course on gear design to be able to understand how stress calculations in operating gear tooth are done. But let me settle this issue by saying that dimensions of all the individual geometrical parameters of the gear are arrived at not only from kinematic considerations but also from stress consideration. In this course we are, in this talk rather, even in your course, in your mechanism course, is not going, you are not going to deal with stress calculations of a gear, right. So, the stress calculations of a gear can be a more involved subject. You can do it as a part of your project probably using some FEM type calculations. You can look up the research literature also. There is enough work done on it. All that I will say is that if you wish to appreciate that, you need to do more advanced studies on this topic. Let me thank you for your interest and patience. So, we will call it a day here. We will meet again in the next session. Thank you.